There was tectonics. As plates collided, the rocks shifted and rose, folding into large mountains, and as the earth lifted out of the water and nature took its course, the rocks weathered into their beautiful shapes. And when submerged again, life made its home. This is Volume 3 of Subnautica, the Rockumentary. Hello again everyone, my name's the Rockumentarist, and in case you haven't figured out yet, I'm very normal about rocks and fossils. This is the third instalment of 4 in my Subnautica Geology series, and this time we're covering the mushroom forests, blood kelp zone, floating islands, mountains and the bulb zone. If you're new here, hi, hello, welcome. You don't have to watch the others first, but if you do like this one, you'll definitely want to watch them too. And if you're returning from my others, welcome back, lovely to see you honey. Right, enough yapper, let's get straight into our first area, the mushroom forests. Unlike most biomes where each part of the biome, even if separated, have the same geology, the two mushroom forest areas actually have incredibly different geology. So, despite me talking about them both in the same chapter, I'll be dealing with them both separately, starting with the forest next to the dunes. This forest is made of the same group of bioclastic limestones we established in the safe shallows that are also part of the underlying dunes, but unlike what we've seen in the other sections of this formation, there's a pretty big rift in this part. In the past we've established these rift-like gaps are likely formed by faulting from the tectonic activity in the area, and with its proximity to the trench, this one is definitely no different. In the sparse reef, I talked about rocks likely metamorphosing from the stresses of this, and this could be the same here, except instead of forming a slate or a myelinite, because our rock here is limestone, this will form marble, a rock formed when any kind of limestone is metamorphosed. Something that piqued my interest a lot is also the fact that mushroom stalks appear to be made out of the same limestone, or some kind of calcite, which begs the question, are these even mushrooms? Well, one Google search actually tells you no, which brings me a lot of peace in knowing I wasn't going insane whilst looking at these things and wondering if I was going to have to pull out another floating island theory moment. See, mushrooms in real life are made of these things known as chitin, which is in their cell walls, but these mushroom stems are obviously made of calcite, a biomineral that does not appear in mushrooms, which means that these life forms growing on the calcite are actually an alien species of coral. They're specifically some weird kind of table coral, and as I found out from the database entry, the calcite stem is also part of the main coral as well, which is good because I couldn't find a good geological explanation for limestone pillars like this. Since the cap is said to be more like earth fungi, it's possible that these corals incorporate chitin into their caps in some method. However, where they find chitin is kind of beyond me. The most I can guess is the fact that the chitin appears in some algae and in isopods, as well as the mushroom forest proximity to the kelp forest, which means that some species of algae in the forest may be chitinous, and their death feeds the corals in the forests, which is definitely a really interesting part of the ecosystem if that's close. Also interesting to note in this part of the forest is all these massive ridge-like structures in it, as well as these mini arches, which, in my opinion, I think is other corals. This tube-like coral, similar or maybe even the same as the ones in the safe shallows, may have also lived in this mushroom forest, before being outcompeted by these tree mushroom corals. Most likely, since the caps block sunlight on the seafloor, these corals couldn't access any sunlight, which would have caused migration of the small zooids that live in these corals, or, as it's well known, coral bleaching. This means these tube corals were essentially outcompeted, and this will be shown in the fossil record, with the tube corals no longer being present in the fossil record of the limestone in future. The reason they still exist in the safe shallows is likely because the tree mushroom corals haven't migrated over there yet, or couldn't settle there, which allowed the tube corals to thrive. Back to the ridges, these are likely the stems of the tree mushrooms and other tube corals combined, likely the larger ones that are then felled in some way. You'll also notice the sands on here are the exact same sands found in the dunes. Just a really neat detail I noticed. Not that important though. At the other mushroom forest next to the bulb zone, the geology isn't as interesting, but it is mysterious. See, I can't quite put a pin on what this rock is. A vague grey rock has always been hard to figure out anyways, but the mushroom forest being situated to two very different geological settings makes this even harder. On one side there's the kelp forest, a sedimentary limestone or chalk, but this mushroom forest is a lot lower down than this chalk despite being a similar colour. On the other side, the mountains made of some volcanics and metamorphics we'll cover later. There's evidence for potential metamorphosis in the area. This section of green rock, for example, is telling, since green is a colour in rocks that only usually appears as a result of metamorphosis, unless it's an igneous rock. But there's also an archway, a feature made in limestone weathering. And what if that green is just more algae? A real head scratcher, if you will. So take what I say about these rocks with a grain of halite. In my personal opinion, I think these are part of the kelp forest rocks, and sometime after their formation they were faulted down, hence the massive drop between the kelp forest and the mushroom forest. During this drop, part of the limestone nearby to the fault, such as the green looking limestone, may have been partially metamorphosed from the pressure of faulting, which caused a small green tinge. Either this or it is just a bit of leftover algae, but the presence of no other algae in the other limestone suggests otherwise. Now if you disagree with my interpretation, do let me know. I'm interested in what you have to say. But for now, since there isn't any other real formations in this part of the forest, let's instead move on to the blood kelp zone. Something you'll immediately notice about the blood kelp zone is it's pretty much all one rock. It's nearly entirely shale, as much as the formations of the rock could potentially say otherwise. Usually when we find shale outcrops, they aren't in these massive cliffs, but they do exist, so I can let it slide, even if it's usually in the presence of other hard rocks. I'll let it slide. Shale cliffs. Shale everything really. It's all shale. You're shale, I'm shale, I love shale. Okay, anyways. These shales are likely rich in plant fossils, absolutely tons of them. And you know what that means? That's right baby, oil shales! As these plant matters in the shales get deeper and deeper, they get converted into kerogen, which with even more pressure and heat becomes oil and gas. And I would not put it past Alterra to start fracking the blood kelp zone the minute they get a hold of this information. First it was the Grand Reef, now the blood kelp zone. None of planet 4546b is safe from the hands of Alterra's desire for greed. Now, since this place is also close to the Lost River, it makes me wonder if any of the leviathans or fish found in the area also have fossils present in the blood kelp zone. This is much less likely, but it's not impossible, especially with leviathan presence in the area. There's also a tiny bit of limestone near to the top that appears to be dipping about 40 degrees, maybe a bit less. Can't really get my clinometer out on a bit of fictional rock. But the actual shale cliffs themselves don't appear to have any dip to them, just horizontal shales. In geology you won't really find dipping rocks on top of non-dipping rocks, just doesn't really work. So my best guess was this shale eroded on this angle, and the limestone was deposited on top. The closest that exists to this in real geology is a buttress unconformity, where a period of erosion happens in kind of a river channel, then new deposits happen on top at what appears to be a dipping angle. But if you look at what forms these unconformities, these usually come back up. It's like a pit almost that the rocks are deposited in. But this rock goes into the void, so guess we don't get to see the full pit. That's the closest I can get anyways. This is likely just another case of we didn't think some geology nerd would overanalyze our rock textures to this degree and the angles we place them at. Which is wrong! Game devs, watch out. I will overanalyze your rock textures. I actually thought I'd mention something that I found post-editing that I think actually would be a really interesting theory for the blood kelp forest. See, as I explained with the buttress unconformity, this means that there may have been a paleo channel there in the past, or in other words, an old river channel. Now what's also nearby to the blood kelp forest is the Lost River, and looking at the other formations in the area, it's possible that the Lost River once flowed exactly where the blood kelp zone is, and then further migrated downwards into where the Lost River is now, and this unconformity could be an evidence of this happening. Now obviously this is quite speculative, it might not be true, but I think it was quite interesting to note. Looking at the blood kelp too, they're likely weakening the rock they're living on. They survive, it seems, by digging their roots into the rock, and shale having a lot of cleavages and fractures and other general weaknesses to exploit, this makes sense. I just don't quite understand how they live on just rock. When plants bury into the rock, they usually have soil on top to sustain themselves, but these kelps just go straight into the shales. Do they survive off the organic matter present in the shales? Because I can't see any other way they could just get nutrient ions for life out of these rocks. Shales are like pretty much all organic matter and mud minerals. Is this blood kelp just so based that it doesn't need any ions, just rock? You know what, no more talking about shale until the bulb zone. Let's just move on to an even more confusing area. You would think in this area where we have canonical geology information, it should be straightforward to tell you what's going on. There is some straightforward stuff about it. It's more of the Safe Shallows limestone formation again, and just like the game tells you, there is evidence of chemical weathering. Just look at it. My gripe is, why is it everywhere? Seriously, every surface of these stupid bits of limestone is covered, all over, in weathering. Weathering happens on the surface of the rock, okay? So only the exposed part, the bit it rains on. It can't rain on every side of the rock. Why is every single side weathered? What did these rocks go through to have every single side of them covered in rain and weathered? I can't for the life of me figure out what way allowed every side of this limestone to be weathered, because in a real life example, only one side of it, maybe 2 or 3 at absolute max would be. Does someone just really like rolling around small island-sized boulders of limestone to make sure every side gets covered in rain? I don't get it. Okay, let's just ignore that and cover the rest of these rocks, which are very boring. Geology-wise, this is probably my least favourite area because at least the crag fields have one type of formation. It's pretty much only limestone with some hydrothermal vents at the bottom, something I've covered a million times in this series by now, and is present in nearly every region. The limestones at the bottom are unweathered and likely weren't exposed at any point, and fossil-wise, these will have the same shells and corals as the rest, but for the additions of bone shark fossils in the future, since unlike regular sharks which only have cartilage, these sharks have hard parts, allowing them to fossilise. And that is literally all I can say about this place. Let's refresh with some much more interesting geology in the mountains. In the last video, if you remember, I mentioned that I thought Subnautica may be situated on a subducting plate boundary, and now is the time to discuss it, because these mountains are part of the evidence. At a subducting plate boundary there are 2 important features to look out for: a trench, like the Blood Kelp Trench, which will be covered in the last volume, and a volcanic mountain system. These mountains often spew andesitic lava and contain both volcanic and metamorphic rocks, from the magma rising through the crust and from the pressure of the plate squishing together. So even though a lot of the rock textures here are just a grey blob, by looking at the shapes of formations and using the knowledge that this is a volcanic mountain range, we can definitely imply what the geology of the area is. Starting on the mountain island, looking at the way this mountain has a steep angle and these deep ridges, I suspect this mountain is an inactive volcano, with the ridges being previous thick lava flows from the silicious magma sliding down the edge of the volcano. Looking at the edge, you'll notice it's oxidized too, from the reaction of iron with the oxygen in the air. As for the caves, I think it's just a gameplay thing. Volcanoes don't usually have caves. However, I am going to immediately contradict myself and talk about the caves found at the base of the island, because as unrealistic as they are interesting. Because this is the first time in covering the geology of this game that I've seen actual evidence of flowstone. I speculated it could be around in the Grand Reef in the last volume, but here we actually have properly textured flowstone in between the stalagmites and stalactites. Unbelievable! Peak rock textures! As I mentioned last video, flowstone is created from water flowing down the rock walls and precipitating, so in the past this area was not submerged. As for the rest of the cave, there's not really anything new to note. I was just very excited to see the flowstone, okay? Now, even though there isn't any active volcanoes, we still have our good friend the hydrothermal vents. And this does make a lot of sense, this is after all a big volcanic area. It's likely underneath this area there'll be lots of these large intrusions called plutons, or even batholiths, where massive splodges of igneous rock exist within the surrounding country rock, often found near volcanically active areas, or Cornwall. In these we'd expect to find lots of coarse-grained rocks, such as granodiorites or granites, and potentially even pegmatites near to where hydrothermal fluids are. There's also a fun rock we may find really deep down called serpentinite, a rock unique to subduction zones caused when the magma underlying these zones reacts to water brought down by the plate, which causes the chemical composition of the magma to change, producing serpentinite. This process is called metasomatism, or serpentinization, and is a unique kind of metamorphism where the change in the rock is initiated by fluid instead of heat or pressure, and this process is incredibly important in the formation of these volcanoes, since it lowers the melting point of the rock, which actually allows it to partially melt, decreasing its density and allowing it to rise through the crust as magma, where it then gathers in volcanoes and eventually comes out as lava. Without this, the magma just won't melt and there'd be no eruption. Not here at least, other places are different stories. And for all of you thinking, what? Isn't magma liquid already? No, it's solid. Sorry. You've been lied to by your geography teachers. As for the other rocks in the area, I mentioned earlier there's metamorphics. The pressure from the plates compressing is likely to produce phyllites and schists, and potentially even gneisses, rocks I explained in the last video. But the introduction of heat also means we have a new kind of metamorphism which produces new rocks. Next to the intrusions, the heat will cause a change in the rocks, with the most changed rocks being right next to the intrusion and the least changed rocks being right on the edge of what we call the metamorphic aureole, the extent of the rocks around an intrusion that have been altered by the heat. Say hello to my least favourite rock, spotted rock. This rock brings out a sense of disgust in me and I can't pinpoint why, but it is important. When small amounts of heat are applied to shale, it produces these large crystals we call porphyroblasts, in this rock often being cordierite or andalusite. Closer to the intrusions, we'll move on to rocks I like a little more, andalusite hornfells. These ones are quite pretty, having larger andalusite crystals that, if you look closely, you may see a little X shape in, a character that is pretty unique to andalusite. If the heat is great enough, there's the potential for seliminite hornfells, where, you guessed it, you get big crystals of seliminite. But these are less likely to form since they require lots more heat, so we'd be looking at likely up to andalusite hornfells. This is also given that shale was present. If limestone was around, there'd be marble, since marble can be formed from both kinds of metamorphism, and if sandstone was around, there'd be metaquartzite, another rock formed by both kinds. We'd also likely have fold structures in the area, as well as faulting. I'll cover folding since I don't remember if I've covered it before in these series. When rocks have pressure applied to them, they bend, producing a fold. These folds can point, if you will, up, called an antiform, or down, called a synform, and they can often come together, especially in mountain ranges. There's other neat things that can happen during folding, such as naps, where a fold at a low angle becomes faulted, but since all these mountains in the area look to be at a steep angle, it's unlikely we'd find these. Geology can prove me wrong though. Also, look at these boulders! They're septarian nodules! Septarian nodules are a type of concretion formed when mud-bearing rocks dry and shrink, which creates cracks that then infill with minerals that precipitate out of water. When cracked open, they produce this beautiful turtle-like shell pattern of minerals and rock, which lots of people find themselves drawn to. These also tell us that the rocks the mountains may have been before being squished could have been a mudstone or shale, since mud-bearing rocks are the ones to form these, but why they're here after metamorphosis is beyond me. Still, pretty cool. The last chapter for this video, and this one gets pretty interesting and speculative. The bulb zone has always been a mysterious and intriguing area to me, so covering this was a fun challenge to say the least. A lot of the first rocks you encounter appear to be the same limestone as the mushroom forest, and have similar structures to the one found in the kelp forest, with arches and caves around. But the more you look around, the more differences you find. Around the hydrothermal vents, for example, are these pockets of shales. I have no idea why. There is nothing to suggest why shale is here, or why specifically only around the hydrothermal vents. My best guess is it's remnants of shale from the pre-metamorphosis mountains area that also happen to the outcrop of the bulb zone, but not be in direct contact with the high pressure applied to the mountains. Since vents are characteristic of the magmatic mountains area, and it's likely the same hydrothermal fluid systems feeding the mountains are also feeding the bulb zone vents, and potentially many other vents around the map. As you move more towards the Lost River, this land dips steeply, almost like a huge gap. This gap, in my opinion, could be a lava tunnel. When lava flows from an eruption, it creates a path as it travels, which can hollow out and produce these gaps, as the exterior chilled lava continues to heat the interior molten lava that eventually drains out, leaving this chilled tube. I visited one myself in Iceland and noticed some similarities, with the rounded shape, dark coloured rock and what potentially looks like basalt columns, similar to the cooling columns you can find in the tunnels. But I don't have much other evidence to back this up other than the nearby volcano. When I explore the Lost River and cover its geology, I may update this theory in the future depending on what the geology in there suggests, but for now I'm gonna stick with this theory. Nearby, another tall structure in this zone also looks like some kind of lava flow structure. The way it's incredibly different to the surrounding limestone, unconforming to the way they're set out, the dark colour and the weird angular shapes, suggest to me that this may be a lava flow that went over the surrounding geology. But again, the rocks in this game can be a little vague, so feel free to add your own interpretation to this structure in the comments. But since other nearby geology suggests lava activity, I'm gonna say that this is most likely some kind of lava formation. Also nearby, interestingly, is our Safe Shallows limestone. Again, it's a more pale yellow colour than our grey kelp forest limestones that mostly make up the bulb zone geology, and it's interesting that it's also found here. Since there's obviously no glacial features around here either, it can't even be some large part of an erratic that was carried by a glacier, it's just here, which is quite cool really if you ask me. Unfortunately, since a lot of the bulb zone is covered just by sands and the big blue plants, this means this video is gonna have to come to an end here. Thanks so much for sticking around for the third volume of the Subnautica Geology series. I think we covered some really interesting areas in this video. The next installment in the series will be the last, with all areas covered, so keep your eyes out for that. A lot of you have asked if I'll cover Below Zero's geology after this, and whilst the answer is eventually yes, I do have other fictional series I'd like to cover before that. Plus I haven't actually finished the game yet. And weirdly enough, Silksong was just announced. And knowing me, I'll definitely want to get a video of the geology of that done before I even finish off this Subnautica series, so you may have to wait a bit for volume 4. I do hope you enjoyed this video though. If you did, please consider subscribing to see more geology and paleontology focused content. Eat 5 rocks a day for a varied mineral intake, and I'll see you again in the next video. Ta-ra!